Okay, so before we do some full-on graphing, what I'd like to do, I can try to get this whole thing in here. All right, so I'm afraid if I lift this up though, I might lose. There we go. And hopefully the picture will stay kind of in there. So kind of a big thing there. So I have 3 graphs, and I've got 3 different manipulations of cosine and sines. All right, so our task is to figure out who's who on this graph. So I thought this would be a great way to kind of to do A, B, C, and D and get a feel for what they are, and then at least compare them before we actually start going and graphing some things. So in this case, A is equal to 3. So we're looking for an amplitude of 3, and the equilibrium, right, C is equal to -5. So that tells us that our equilibrium, right, is going to be y equals -5, and our wave is bouncing back and forth between 3. So we could probably just use that by itself to kind of figure out who's who, right? Because if we go look at the graph right here, everything is bouncing back and forth around y equals 0. Here, right, if we take a look at this graph, its high point and its low point, right, its high point is, hopefully you can see those numbers as 8, and this low point is 2. So the halfway point is going to be 5, right? And so here, our equilibrium is y equals 5. And then down here, we're going from -2 to -8. So the halfway point is right here, right, at -5. So just by looking at the equilibrium by itself, right, we can see that this one's a good candidate. It also matches A equals to 3 because we got 1, 2, 3 units above the equilibrium and 1, 2, 3 units down. So the graph, the wave, is 3 units above the equilibrium, 3 units below it. 3 above, 3 below. 3 above, 3 below. 3 above, 3 below. All right, so this is a good candidate, right? This looks very much like y equals 3 cosine of 4x minus 5 just by looking at amplitude and the equilibrium shift. However, let's look at the other things. B is equal to 4. So that means our new period, right, is pi over 2. So if we look at this graph, right, it's hopefully not hard to see, but what a cosine graph does is it starts at a high point, goes to a low point, it comes back to a high point, right? That's a classic cosine graph, and it is occurring, right, between 0 and pi over 2. So that normal cosine action of starting at a high point, going to a low point, and coming to a high point is happening between 0 and pi over 2. As a matter of fact, it repeats the action, right, in another interval of pi over 2, and in another, and in another. So it basically goes through 1, 2, 3, 4 cycles on a normal 0 to 2 pi. Right, so it's been packed in, right, by a factor of 4 like we did in our computation there. So that also matches that. And then the D is equal to 0, right? We're not adding or subtracting anything to the x. So there's no phase shift. So that's why that high point is occurring right where I expect the cosine to do, right? Along the y-axis, cosine usually begins at 1 or at its highest point. And then it goes down, and then it comes back up at the end of the cycle. So this pretty much matches in this little area right here. Let me highlight it in red. And I apologize, to get the whole graph, how about I do this? Right, so that way you guys can see those numbers a little better. All right, so we've got that one, and we can see everything we want to see. So in this little thing that I'm highlighting in red, everything I want to see is there. We're going from 0 to pi over 2, so the period is pi over 2 as expected, right? Because B is 4. We can see the equilibrium as y equals -5, and then we can see the amplitude right with 3 above it and 3 below it as we move along and along. So great candidate for that one. So let me shift back out here. So what about the next one? Sine graph, right? So here again, we're looking at an amplitude of 3, and we have C is equal to 5, so we're expecting y equal 5 to be the equilibrium, and with just that with that information alone, we know this is our graph, right? This is the graph of y equals 3 sine of 2x plus 5. because it matches those pieces of data. The equilibrium has shifted up to 5, and the wave is 3 above, 3 below, 3 above, 3 below, right? 8, 5, and then 2, 5, and then 8. So we keep bouncing back and forth. Actually, 1, 2, 3, yeah, 3 units above, 3 units below. But to see the other action, right, B is equal to 2, right? So that means our new period is pi. And so a sine graph, what it does typically is it starts at 0, 0, goes up, back at 0, goes down, and back here. So you see that happening. That's pi right there, right? And 0. So it does seem to be happening along an interval, right? We just highlight this portion right here, right? That sine wave, right? That's a good sine wave action. Starts on the equilibrium, goes up, comes back to the equilibrium, goes down, and then comes back to equilibrium. That's a classic sine graph happening from 0 to pi. When we usually anticipate it, right, here's 2 pi out here, right, to right there, and you can see we're actually going through 2 cycles over a normal period, right? That's because we've halved the period, right? So old period's 2 pi, and now it is pi. So we're going to go through 2 cycles when it used to just take us just 1, right, over 2 pi. So that's what's happening there. And then, of course, in this action here, D is equal to 0, so there's no phase shift. And we see that happening because this is occurring, right? The sine curve is doing what it's supposed to be doing, right, under normal circumstances. It starts at its equilibrium and then comes up, back at equilibrium, comes down. You can see the quarters happening, if you would, right, through the graph in that one thing. So all the action. So by process elimination, this graph up here must be the y equals 3 sine of 2x minus pi over 2. So let's just kind of see that action happening, okay? Oh, for starters, I just realized something. This graph here, I think I need another set of parentheses in there. I apologize for that. Okay, I think that'll... Actually, no. You know what? I know what I wanted to do. We first have to, if we factored out that 2, right, that'll actually become pi over 4. So you got to be careful of that. And now I just remember what I want to do with this, right? So I started with 3 sine 2x minus pi over 2. But we usually want a set of parentheses around that. So if I factor the 2 out, that tells me that b is equal to 2. But by factoring the 2 out, right, I got to divide, basically got to factor that 2 out of here. If you just remultiply it, 2 times x is 2x, and then 2 times pi over 4 just gives us pi over 2. So this tells us that d is pi over 4. So putting this all together, a is 3, so there's your amplitude. C is 0, so y equals to 0 is my equilibrium. So far so good, right? My equilibrium is 0. We're bouncing 3 above and 3 below. And then my b is 2, so my new period is 2 pi over 2, which is pi. So we can see basically, it's probably easier to see it from high point to high point. Notice that that's occurring at a pi length, right? Or from here to here. But that's where the phase shift is coming in. D is equal to pi over 4, which means we're moving over to the right, pi over 4. And that's where that point is there. So if I block this, right, there's basically, when we were doing our sketching, that would be our first cycle for this sine graph. And notice it's starting at a low point, hitting a high point, coming back to the equilibrium, starts at equilibrium, goes to a high point, comes back to equilibrium, goes to a low point, comes back to equilibrium. So that's a classic sine graph, and you can see this is starting at pi over 4, the phase shift. And so that means it's ending right here. That would probably be 5 pi over 4, right? Subtract the 2, you get pi, right? So pi there, alrighty? And so you can see all that action occurring just on that piece of cycle. So there it is, seeing it to a graph. Now, right, let's go do the big thing, right? Let's start off with some equations. Where are those things at? Let's start off with some equations. There they are. Right, let's go graph some equations, and that's what's coming next here very, very shortly.